Okay, welcome to a review of Homework 7, Problem 2. This is problem 8.046, two slender rods connected by a pin. So the problem states we have two slender rods of negligible weight that are pin connected at C and attached to blocks A and B, each with a weight W. The value of theta is 80 degrees and the coefficient of static friction between the blocks and the horizontal surface is 30 degrees. And then the two things that we have to do for this problem, we need to create free body diagrams of pin C, block A, and then block B. And then we also need to use the knowledge given to us in this problem to determine the largest value of P for which equilibrium is maintained. So once again, before we start, it's a good idea to go through the problem and figure out what we actually know about this. So we can go through and get notice assumptions. So one major assumption is that the rods are slender and of negligible weight. We also can note that the value of theta is 80 and that the coefficient of static friction is 0.3. So using that information, we can fill out our little knowns table here. So we know that theta equals 80, mu equals 0.3. And then we need to determine the largest value of P. So we have to figure out what P equals to maintain equilibrium. So once again, maintain the largest value for P, which maintains equilibrium, means motion is about to occur but has not occurred yet. So once again, we're able to approximate friction in the same way that we did in problem 1. And then we can proceed using that assumption of max static friction. So the first thing we're going to do is create 3 FBDs for pin C, block A, and block B. So if we look at pin C first, what we're going to have here is this little diagram on the left. So what happens is we have the force P acting, and just for visualization, I cut rods A and B and then denoted them with points D and E. But what's happening here is that there's going to be two forces in those members. So we'll have force of C on A or vice versa, or force A on C, they'll be the same. And then we'll also have another reaction force of CB, so force CB. So those are the 3 that are acting on pin C. And then we can also look at block A, which is this one in the middle. So block A here, we have just the weight of the block, denoted as W. We have the normal force, which is pointing directly up because this is a flat surface, or it's perpendicular to the surface, and the surface is horizontal. And then we have the force of friction. And once again, we're assuming, I would suggest looking at this diagram and trying to visualize, okay, if motion were to occur, what direction would A move? And in this case, so say P is moving down that way, you're most likely to get A and B to move outwards. So that would mean that A is moving this way and then B is moving that way. And that's just important to note when you're creating your friction value if you want positive values that are slightly easier to work with. So with that, we have the force of friction, and then the last one is FAC. And then the problem gives us that angle for us to use. And then we'll go through and do a similar thing for block B. So with block B, we have FBC. We have the weight of the block, and then like block A, we also have a normal force and a friction force. And like I said, the blocks will be pushing out. So if block B is going to the right, that means the friction force will be going to the left. So what we can do after we make these diagrams, just denoting the forces, I'll just clean it up a little so it's a little easier to see what's happening and more representative of what they're asking. So after we have our 3 FBDs, we can move on to the second part of this question, which is determine the largest value of P for which equilibrium is maintained. Okay, so in this one, we can look at each FBD to help us get some information about P, right? So let's start off with C, which includes P in the expression or in the diagram. So for C, what we can do is we have our FBD, and then we can actually rearrange where the forces are pointing, or just so they're all still meeting at C, but we're just slightly changing their location so we can create this triangle. The reason this is 20 degrees here is if we just move we know that this is 60 and this is 80, so we can actually just subtract the two to get that angle between them. So now that we have our little triangle, we can use our knowledge about sines and cosines to isolate FAC and FAB. So now we have two arbiter forces in terms of P, which is going to help us later on to figure out what exactly our max P is. So after we have that, we'll move on to the second FBD, which is the FBD of A. So for A, what we have is is we can go about it the standard way, which is just creating our summation of X and Y equations. So yeah, once again, the oriented, however, is easiest in this case. It's pretty standard X, Y. So just take note of the forces acting in the X direction. So that's FA and the X component of FAX, or sorry, FAC. And that'll get you this equation here. And then for forces in the Y direction, we have the normal force pointing upwards. And the normal force pointing upwards here. And then we have the weight going down, and then this vertical component of FAC, and that'll give us this equation. So now that you have all of that, what you can do is you can go through and figure out what those, you can rearrange them slightly. So once again, we have expressions that are only involving W and P. And the reason for that is when we have equations that mainly involve W and P, P is what we want to know, and then weight is the information that we have. So second part of FBD of using our FBDA is we know that the force of friction equals mu of S times N of A. That means that we know N of A equals the force of friction force of A divided by mu of S. And we also know that we know F of A over mu. We know those two quantities separately. And we also know N of A from up here. So we can actually set those two equal to each other and use that to obtain an expression. One of the possible expressions for P. So this gives us that P is 1.255 W. So we cannot stop here because we also have to check how P affects block B. So we'll do a similar process for that. I would stop the video here and try that and set that up and determine what your P is, what your P equals, and then I'll go over that. Okay, so hopefully I had a sec to do that. So after, it's a similar process as the process for block A. And then when you go through that same process, you'll find that P equals 1.32 W. So if we're looking at those two conditions that we have, we are comparing those two values that we found. So P equals 1.32 W and P equals 1.255 W. And the problem above is asking us to determine the largest value of P for which equilibrium is maintained. If we look at those two expressions, whichever, both of those must be true for the system to be in equilibrium. That means we have to choose the smaller value. Therefore, we know that P max is equal to 1.225 W.